Today we're going to look at transformations. So in Algebra 2, you worked through all of these, so this is a lot of review, and there's just a few extra things that the book will ask you, or that we'll look at today, that are further than what you did in Algebra 2. So in this first section here, I just went ahead and wrote out all of the transformations that we'll use. So these apply to any function. These will apply to any function in trig or anywhere where you have to shift functions around. So vertical shifts are going to be adding or subtracting a number to your function. Horizontals will be inside the function. So I'm looking at this now. Reflections are on the outside of the function. Over the y-axis, there's going to be a negative x inside the function. Vertical stretching occurs when you have a c value multiplied by the function. And vertical shrinking is going to be where that c value is between 0 and 1, so it's a fraction. And these are much easier to work with rather than talk about, so we're going to go straight to the examples. Okay, so for the first one, choose a color here. The parent function, I have this question here. So what is the parent function for this function? Well, it's x squared. And so it's important to know that because it makes it a lot easier. We know that the general shape is this parabolic shape. So we're going to apply transformations to that. Remember, these are always reversed. So you did this before, but if you have a -1, that's a shift right 1 unit. Okay, this 3 is a vertical shift. And I'm going to actually say shift up 3 units. So what we're doing is taking the shape of the parabola and we're going to shift it right 1 unit and up 3 units. So I always like to look at these like they have an anchor point, which is down in the vertex of the parabola. So to graph this, let's call this the y-axis. This is the x. Actually, this would be f of x. Okay, so the vertex shifted 1 to the right and 3 units up to be right there. Okay, there's no vertical stretch or shrink with this function. So what we do is apply that pattern that you learned in Algebra 1 and then also used in Algebra 2, which is from your vertex, you go over 1, up 1, over 2, up 4. To the left, we do the same thing. So it is a symmetrical function. It looks the same on both sides. See if I can graph that. And so that would be the transformed function f of x. And if you had a question about that, like where did this point at 2, 4 come from? If you plug in a 2 into the equation, you'll see that you would get a 4 out. So these points are all just going to be found from plugging in the numbers. But right now I'm just creating a general shape. So I don't want to enter a number every time I want to graph something. So every point doesn't have to be entered into the function. We just want to graph a general shape. So right now I'm just going to say this about a reminder. So normally this will just be a quick sketch. We would have an axis, and let's say that we did or graphed the function x squared. I missed that point, that's okay. So normally the coordinates for x squared, like if we were to, let's say, put it in a t-chart and do some values here, we plug in an x, we get x squared out. So normally we would have 0, 0, 1, 1, 2, 4, 3, 9, 4, 16, and so on. So we're squaring the number. So if you look at our graph here, this point is at 2, 4. And so we'd have another point at 3, 9. So when we're looking at transformations, we're just taking that shape and applying things to it. So in our next example, we're again going to use this x squared. So our parent function would look like that. And let's just talk about the transformations. So this 3, this is up 3 units. This 2 would be right 2 units. Remember, the sign is always reversed. So if it says +2, you go left. If it's negative, you go right. This negative sign is a reflection over the x-axis. And then the 1/2 is going to represent a vertical compression by a factor of 1/2. So that's the way you'd say that in words if you had to say it. A vertical compression by a factor of 1/2. Okay, on the graph, I'm going to go ahead and graph my vertex first. So it's Precalculus, it has a vertex. It's going to be right 2 units and up 3 units. So that would be my coordinate for my vertex. This function is reflected over the axis, so we're going to get off to the side here. If I were to graph negative x squared, it would be upside down like that. So that's the general shape it'll show. The factor of 1/2, normally, just like I showed you right here, we'd go over 1 and up 1. Well, right here, instead of going over 1 up 1 or over 1 down 1, the 1/2 cuts that number in half. So we're going to go over 1, down 1/2, both sides. And I mean down 1/2 from the vertex. And so over 2, normally we'd go down to -4, but instead what we're going to do is go down to -2. And that's 2 away from the vertex. Normally we'd go over 3, down 9. For this one, we're going to cut that 9 in half, so we'd go over 3 and down 4.5 units. So if I sketch that out, it gives me a parabola that looks like that. So that would be our graph. The only thing it didn't do there, which I don't like, I should say f of x equals. Okay, let's do another one that has a different parent function. So in this case, it's the cubic function. So the cube, that would be our algebraic representation. And then the cubic function does this, or has that sort of general shape. So let's look at our transformations here. The -2, that just shifts it down. Fix that too. Shifts down 2 units. This 3 is a vertical stretch by a factor of 3. Okay, so normally if we had this cubic function, this is what we'd do. We'd say, okay, plug in an x, we get an x cubed out. Plug in 0, you get a 0. Plug in, plug in a 1, you get a 1 out. Plug in a 2, you get an 8 out. And if we go the other way, then my table's not going to be in order. But if I plug in a -1, I get a -1. If I plug in a -2, I get a -8, and so on. So those are the original points. So what I'm going to do with this one is take my first value. By first value, I mean, so all of these functions have an anchor point of sorts. So this one always goes through the axis at 0, 0. So in this case, our function, depending on what we have here, it might not go through 0, 0. And you can plug in a number to check it first. So f of 0 would give us a -2 in this case. So we would take our origin point and move it down 2. Let me designate these as having a value of 1. Okay, so this is now where my graph would be centered. Normally, we would go over 1, up 1, for this function. But since we have this factor of 3, it's going to be over 1, up 1 times 3. So I would have a point here. Normally, from that origin, I would go to the left 1 and then down 1. But again, this factor of 3, it's going to multiply that by that much. Let's see if we can even fit another one on here. I think we can. So from our origin point again, normally we'd go over to up 8. Well, as you can see, that won't fit because we'd have to multiply it. So our graph as drawn would be too small. So let's just draw this general sketch like, oh, missed my point, that's okay. It's the best I can draw on an iPad right now. So that would be a general representation of that. Now, it's not a perfect representation, but we have taken a cubic and shifted it in general. So these graphs aren't based on superior accuracy. They're based on getting a quick visual on what we're looking at algebraically. For our next example, we have a different kind of function. We have the square root function. The parent function is root x. And I'll do this little t-chart again, kind of like that. So I plug in an x and I get a root x out. So if I plug in negative numbers, it's undefined. So this is only going to be defined for positive numbers. So what I do is plug in those numbers, plug in a 0, get a 0. So this has that, its anchor point that I like to call it. It's anchored at 0, 0. Then we plug in a 1, we get a 1. And let's choose numbers that work for this. So at 4, I get a 2. At 9, I get a 3. So I'm choosing numbers that are perfect squares, so it's easier to work with. Okay, so this one might not be fun to graph, just because it's harder to get accurate points on it. Okay, so let's just talk about the transformations again. So the 1, this shifts the function up 1. Every point is going to go up 1. This -4 does the same thing it would do in a square x squared. It's going to shift it right 4 units. And then the 2 does a vertical stretch by a factor of 2. So that's a really hard one to represent, sketching a graph that is a square root function. Because the square root function looks generally like this line over here. Okay, that's like its general shape. So let's just work with this. So what was once at 0, 0 is now going to have, it's going to be shifted up 1. So this doesn't, so let's talk about that. This doesn't have a vertex, but if you look at our function right here, it looks kind of like a the x squared function, quadratic, I couldn't think of the name. So the vertex number, if you look at that, if this were a quadratic, it would be at 4 plus 1, 4 comma 1. So what's going to happen here is it's going to move that point that we start at 4 over and up 1. Now, normally from this point, if you look at our chart here, we'd go to the right 1 and up 1. But since we have this factor of 2, we're going to go over 1, up 2. Okay. And let's see here. This one's harder to draw, but let's check our next value here. Let's see if we can get something out of here that works. So this one is going to be one where we would have to have a value at 8. Let me extend that line a little bit. So the square root function is definitely harder to graph. I'm also going to take this table and we'll move this around. Need more room over there. Okay, so at 8, if I were to, you can think about this as if we plug in an 8 into the original function, it would be a value of 5. Okay, so this function is going to be something like that. Again, those are a little bit harder to sketch than quadratics and cubics. All right, so this is just another type of question you're asked. So it gives you this generic f of x function, and it says describe in order the transformations on f of x. So if you guys remember the PEMDAS, we're working with PEMDAS here and we describe transformations. So we go in order. So we work from the inside out, from the parentheses outward. So this would be, if I describe in order, the first step applied to this function would be the 5. So this would shift right 5 units. The second, if I work inside out, is going to be this 2 out front. So that's going to be a vertical stretch by a factor of 2. And then our third would be to shift. I'm just going to make that easier. It goes up 1 unit.